Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to the second module for this week. And the first module, as you may recall, explained that this idea of the second law of thermodynamics, and in order to comply with it, said one of the basic relations that must be observed is that whenever from a reservoir you take an amount of energy E or you dump an amount of energy into it, this absorption and emission processes, their ratio must be related by this exponential. And what that means is, if energy is much bigger than kT, that's a small number. What that means is absorption is much harder than emission. It's much easier to emit than to absorb. And this is something we are all kind of familiar with, actually. I mean, so familiar that you often don't think about it. You sort of just assume it. For example, if you had say, consider a hydrogen atom or something like that with two levels. Say this one S level and let's say the 2p level. So it has one electron, which is usually in this lowest energy, the way you think about it. Now, if the electron were here, if the electron happened to be here, we know what would happen. It would immediately emit light and come down. That's the process of emission. On the other hand, if the electron is here, it doesn't easily go up. It usually stays there. Okay? And that's related to this basic point that, you're trying to exchange energy with these surroundings, this reservoir of photons and this bath around you. And it is much easier to emit than to absorb. See? And that is why usually, again, a system left to itself, you say, well, everything just goes to its lowest energy. But if you think about it, it's really not that obvious. Although you hear it so often and you get used to it, well, it all goes to the lowest energy, that you never think about it too much, or you're almost embarrassed to ask why. See? But if you think about it, you see, what kind of a process is it that will let you come down easily but not go up? Because usually mechanical things are reversible. If you can go one way, you can also go the other way. See? Now, the way you can understand this is by saying that, well, I have this bath around me, this reservoir around me, and let us say we plot the energy, the density of states of this reservoir. So this axis is energy, and here I'll write what I call this W of E, and W means the number of states available, sort of like the density of states we had before. So it's the number of states available at a given energy. And the point is that, you see, if, let's say, this energy difference here, if you is, I guess to distinguish from this E, let me call it, say, epsilon. So this epsilon is this energy difference between the two. So what that means is that if the electron jumps down, then the reservoir must gain in energy. And all normal reservoirs will have a density of states, or this available states, that increases with energy. That is, more the energy, more the number of states that are available. And so, if, let's say, the electron is in the upper state, and that corresponds to, let's say, this reservoir having some energy E0. So that's this. That's one. And when the energy is in the when the electron is in the lower state, that corresponds to the reservoir being in an upper state with more energy. So this is E0, that's E0 plus epsilon. Okay. So when the system loses energy, the reservoir gains energy. So this connects to that, this connects to that. And the basic point that makes emission easier than absorption is just that you see, the process of emission means you're going from here to there. And you have a lot more states up here than you have here. So you might have, let's say, just to put some arbitrary number, say you have 10 states here and you have 1,000 states there. So what that means is, when you're trying to come down to this, it's like you have 1,000 of these states. Because when you think of the system and the reservoir as one big thing, here this is one level, but it's associated with 1,000 things here. Lots of states here. Whereas when it is up here, there's only 10 states, just a few. So the reason then, from this point of view, that you can go down much more easily, that you can emit much more easily, would simply be that when you're emitting, it's like there's lots of states. It's like here you are just in some 2 or 3 states or 10 states, and now you have hundreds of states to go to. Whereas going the other way, it's like from hundreds of states trying to squeeze into 10. And that's then basically what gives rise to this asymmetry. The fact that this density of states is higher for more energy. Now, this is where what you might think is, well, earlier in this course, actually in part 1, we talked about the density of states. And at that time, if you remember, we saw that the way we calculated density of states was by writing the energy. We said that, the number of states available up to a certain momentum p can proportional to p to the power this number of dimensions. Remember, we introduced a variable called n of p. This, I believe, was in week 2 of part 1. And if you look at your notes, this would be what's lecture 5 of the notes. And we said that there's this n of p is like p to the power, the number of dimensions. So in 1 dimension it was p, 2 dimensions is p squared, 3 dimensions is p cubed. And which you could write as energy to the power d over 2. Because E is proportional to p square, usually. So what that means is p is like square root of E. So you could write it this way. And then when you take the derivative of that with respect to energy, that's how you usually got the density of states. That would be like, when I take the derivative of that, you'd pick up a e to the power d over 2 minus 1. When you take the derivative, you'd have that minus 1. And this gave us density of states as 1 dimension, 2 dimensions, and 3 dimensions. And you might say, well, then it looks like you said density of states always has to be an increasing function of energy. It's not clear that it would always be increasing, because after all, if d was 1, in 1 dimension we know that this is like e to the power minus half. And that actually would be a decreasing function of energy in 1 dimension. But the point to note here is that when we draw this density of states here, and this is an important conceptual point that we'll talk more about actually in the next 2 modules, is that when I draw this density of states, it's not that due to 1 electron. It is due to this entire reservoir consisting of many, many particles. The one possible model would be you have a reservoir with hundreds of electrons in it, which are all exchanging energy, which have all various states available, and you're writing the density of states for that entire multi-electron system. And in that case, the way you can think about it is as if, you see, usually we say that it's p to the power d because d is the number of dimensions, 1, 2, or 3. But now you can think of it, let's say you have a very large number of electrons. So let me call that n. So n number of electrons. Nothing to do with this. This was the number of states we were counting, but I won't be using this anymore anyway, so just drop that. So you have this reservoir with n electrons. You could view it almost as if it is a system with n times d dimensions. D is, let's say in 3 dimensions, it's like 3 dimensions per electron. So overall it's like nd dimensions. So you could write this as e to the power nd over 2. And this would, the density of states would then be like e to the power nd over 2 minus 1. And since this is a very big number, I don't really need to worry about the minus 1. So in this context, you would say, well, this density of states, W, that I've introduced is like e to the power nd over 2. You see? And then you can see it is an increasing function of energy. Now, how do we get, what I next want to explain is how you get this particular relation that we had stated. So the way you could do that is, you could say that, well, P, let me just get that. When you're trying to write P of E divided by P of minus E, actually, let me just start over there, right here. So, probability of absorption and emission, and one of them, you see, when you are absorbing, that corresponds to the density of states here, and the emission is the density of states there. So you could write it as WE0 divided by WE0 plus epsilon. And this is where we'll introduce this concept of entropy. And the entropy is defined as, let me write it here, is S is equal to K log W. So this is a very important relationship introduced by Boltzmann. In fact, this K is the Boltzmann constant that we have been seeing so many times in this course. You know, KT, they always appear together all the time. And it relates a microscopic quantity like W, which tells you the number of states at the microscopic level, and relates it to a concept entropy, which is actually a macroscopic concept that people can measure at a macroscopic level. Okay, so this is the S equals K log W. What that means is W is equal to exponential S over K. So you could use that here and write this as e to the power S of E0 over K divided by e to the power S of E0 plus epsilon over K. And I could use this then to write it as exponential of, let me find a better pen, minus S E0 plus epsilon minus S of E0 divided by K. So I just took this up, wrote it this way. And now the point is that when you're this entropy function, you see, that's like what I had drawn earlier was W, and now we are using this concept of entropy, which is S equals K log W. And W is increasing, so is the entropy. That's also an increasing function, see? But usually we are talking of a big reservoir where this change is small. So what we could do is, we could say that the change delta S, that is S E0 plus epsilon minus S of E0, that's the change in the entropy from one energy to another. If you divide it by the change in the energy, that is approximately ds dE. That's delta S over delta E, which for small changes you could call ds dE. And this is the quantity that is defined as the temperature, 1 over T. This is temperature, see? And so the delta S, this quantity, is like epsilon over T. And then you see you get e to the power minus epsilon over KT. So what you showed here is, actually, I guess I didn't use E, I used epsilon in order to, separate it from this axis that I had labeled E. So this is really P epsilon. And what we just showed is the relation I had stated earlier, namely absorption to emission is e to the power minus epsilon over kT. But the basic point is that the reason absorption is different from emission, one is more than the other, is because this density of states, this W, is bigger here than here. And what you define is this quantity, this entropy, which is like log W, proportional to log W. And temperature is like this derivative of ds with respect to E. Now, earlier, I had written down, I said if you took a simple model, you could, of this reservoir as being lots of electrons, n electrons, then you could show that this W would be like e to the power nd over 2. Well, from this, if you get entropy, S, it would be like K times log W, you see? And when you take the logarithm of this, you'd get nd over 2 log E. And so, if you now look at what you mean by temperature, 1 over T is ds dE. What you get is K times, nd over 2E, because logarithm of E, when I take its derivative, I get 1 over E. So the point you can see then is, if you just rearrange this a little bit, you'll get kT over 2 is equal to E over nd. And this kind of gives you a feeling for what this new thing that we have defined as temperature, what it means. You see, what it says is, this is the total energy of your reservoir, this is the number of electrons, this is the number of dimensions, or sometimes you could call it the number of degrees of freedom, you see, of E per electron. So it is like the energy per degree of freedom is half kT. And this is one of the very important key results of equilibrium statistical mechanics. That the idea is that when you have a system at equilibrium, the total energy is divided equally amongst all its degrees of freedom. See, and half kT is this energy per degree of freedom. See, and overall, then, whenever you bring two systems together, what happens is the energy exchange takes place in such a way as to distribute the energy equally amongst all degrees of freedom, essentially. Okay? And it is driven by, and these are all driven by entropy. That the basic relationship that I had stated earlier, why emission is easier than absorption, is because, again, it is driven by entropy. And in general, this is why, you see, at low temperatures, we had said earlier, things always go to the lowest energy state. But in general, there is a principle that at any arbitrary temperature, things will go to its lowest free energy. That is, there is something defined as free energy, which is this E minus Ts. And if you are at zero temperature, you are going to the lowest energy. But if you are at some non-zero temperature, then you're going to this lowest free energy. Now, how do you show that? Well, the idea would be something like this, that when I bring two things into contact, so I've got some system here with some energy E, and there is a reservoir with some energy ER, and together, when I bring them together, the change in energy of one and the change in the energy of the reservoir, that must be zero. On the other hand, see, when energy is exchanged, the entropy of these states, of these systems will change, because the number of states that are accessible, the W or the WR, those now will be different, and S equals K log W. So this delta S plus delta SR that is sort of a measure of the overall states that are available, that what was the change in the available states. And the thing is, things are always driven in such a way as to maximize it. It is always going towards configurations with more states being available. And so this always has to be greater than or equal to 0. And between these two, what you can show is, the result is that the free energy, that is, if you look at the change in the free energy, that will always be less than or equal to 0, which means free energy will always be minimized, and the free energy being E minus Ts. Now, how do you show that? Well, from here, the way you could do it is, you could say that, well, delta SR, that's the change in the entropy of the reservoir, is given by delta ER over temperature. Because, we define ds dE as 1 over temperature. So delta SR is this. And then we note that the change in ER, energy of ER, is actually negative of the change in the energy of the system. So I could replace this with minus delta E over T. See? And then, you see, you get T delta S minus delta E is greater than or equal to 0. And we just defined F as E minus Ts. So what we have written here is like the negative of delta F. So you could write this as negative of delta F is greater than or equal to 0. And what that means is delta F must be less than or equal to 0. That's because, you see, if minus 4 is greater than minus 4 is less than minus 3, then 4 is greater than 3. So when you use this sign, it kind of reverses this inequality. So the basic point then here is that when you bring things together and they exchange energy, then these processes are all driven by entropy, something very different from mechanical forces that we are used to. These are driven by entropy, which means driven by trying to get into configurations with more states in them. And the result is the system then wants to go into a state with minimum energy, that, as we explained before, and that's the thing we always are kind of used to, that things always go to the lowest energy. But then at non-zero temperatures, it's really more the lowest free energy. That's where F is defined as E minus Ts.